what I would like to talk about right now is the concept of functions depending on one or two or three variables that may be treated like vectors. How can you use how can you generalize inner products to these functions? Inner product or addition of vectors, all the properties of vectors, how can you generalize it to functions? So suppose, for instance, there is a way to construct a finite dimensional vector from fx. You simply say that x is between, say, 100 and 0. It's an example. And suppose that epsilon is equal to 10. So from that function, we can construct a 10-dimensional vector, for instance, defined as f0 times 10, f10 times 10, and so on. So you have, this is I equals 0, I equals 1, and then you have 10i times 10, and so on. So you can have a vector with 10 components, a finite vector with 10 components. You extracted it from the function. So the components, let's say the vector is given by v1, v2 to v10. So vi is given by let's start with 0. Epsilon times, you have 10 times I. So each of these components is given by this formula. So 0 to 9, there are 10 components. And so when we take the inner product of this vector, suppose you have another function that then gives another 10-dimensional vector. Given by, well, the formula is still the same. Then you can take an inner product between those two functions. Between those two vectors is given by vi wi a sum over I. And you will find that it's given by, oh yeah, so I'd like to correct myself. Suppose that we want to scale the components by square root of epsilon, we wouldn't want to scale it by epsilon itself. It's just gonna give the same vector, but stretch our that's been squished a little bit. So let's correct the formula. This is like a defining way. It's we define these vectors. We define the process of extracting vectors from functions. And so the inner product would be given by And so it's just simply equal to so what would happen if you took epsilon to be a smaller number? Let's say instead of 10 you want it to be equal to 1. And so what would happen is that instead of a 10-dimensional vector, you will extract from these two functions two 100-dimensional vectors given by, so for this one you would have, say, v100 where vi is given by f epsilon I square root of epsilon, which is simply I, which is simply fi. The same for extracting a 100-dimensional vector from that function. So it's given by so when you take the inner product between those two vectors, it will be given by so you can see something that's starting to happen with when we extracted 10-dimensional vectors, the inner product was given by this, and there was a factor of 10. As I reduced epsilon from 10 to epsilon equals 1, you find that the extracted vectors have this form. So you can see that the inner you can see that the inner product that we defined in quantum mechanics, this is an inner product for a complex vector, but you can see that there's a product of the two functions similar to a product of those two functions. So you can see that as epsilon goes to 0, the inner product would actually be given by one-dimensional domains. So for x equals 0 to x equals 100. But you can repeat the same process by enlarging the domain. X can be larger than 100, and small x can be smaller than x. So before going further, let's generalize the procedure of constructing a n-dimensional vector from a function. So suppose that the dimension is n, then from f you can extract a vector given by f. Epsilon is defined by the domain in which the function is defined. So let's keep that domain 100 and we can generalize it for more general domain. So to extract an n-dimensional vector from fx defined only for x from 0 to 100. So we form epsilon, which is given by 100 divided by n, and then we write the vector components and vi is given by, so suppose we start by f0, then f epsilon, f2 epsilon, and so on until you reach, this is 1, 2, 3, so until you reach f n minus 1 epsilon, which is until you reach n dimensions. So vi is given by, so I starts by 0. We can extract a vector from that function, an n-dimensional vector, by that formula given. So we take epsilon times I, and I is going from 0 to n minus 1. So, and let's not forget to add that, which will play a role in inner products. So this is how we define the extraction of a vector from that function. So now let's do the same thing for another function. So let's call that w. So wi, oh yeah, so let's say that we start by 0 and we finish by n by 1, n minus 1. It's a n-dimensional vector. If we count all the components, it will have n components. So yeah, my mistake, sorry. So let's start by 0 and finish by n minus 1, n components. So wi is given similarly as epsilon I square root of epsilon. So when we take the inner product between the two n-dimensional vector, it will be a sum of f epsilon I g epsilon I times epsilon, because it's squared, so it gives epsilon I from 0 to n minus 1. So this is really interesting, because suppose we said that epsilon is given by 100 divided by the dimension. So now suppose that, so yeah, so suppose you started with f0, then f10 until f90, I guess. The increments is you add epsilon, this is, you add, this is going from I equals 1 to I equals n minus 1. So this is the range of the domain of fx gx. So what would happen if the dimensionality was to go increasingly high, which would mean that epsilon would decrease. So as epsilon tends to 0, the number of dimension tends to infinity. So what would happen then is that the inner product of that infinite, of those two infinite vectors with a dimensionality that tends to infinity, will be given by this summation will become an integration, because this epsilon will tend to 0, while the summation will go from I equals 0 to I equals n minus 1. But as epsilon goes to 0, n tends to infinity. So this tends to infinity. So as a limit, you will obtain that the inner product will become simply an integral.